You unbox a $300 fragrance. The glass is heavy, the label is pristine, and then a dark, viscous fluid weeps from beneath the metal collar. Perfume houses spend years dialing in the exact chemistry of oud and bergamot, yet the mechanical delivery system, the bottle, the pump, the cap, is often treated as a last-minute sourcing task. This neglect manifests as half-empty bottles, caps falling off in handbags, and atomizers failing immediately. These tactile failures immediately recontextualize the brand. When the hardware fails, a premium price point feels illegitimate, regardless of the scent's quality. While these often look like random flukes, tracing the failure usually leads back to a specific set of design choices made months before the bottle was filled. From this perspective, a leak is rarely an accident. It is the predictable outcome of structural mismatches in the packaging components. Understanding why a $300 bottle acts like a $12 drugstore spray requires thinking like a mechanical engineer, not a fragrance designer. The customer sees a ruined unboxing. The brand sees ruined economics. This chart displays the profit margins of 10 successful sales and how quickly those gains are erased by the cost of just one returned unit. For luxury SKUs, one defective bottle can swallow the margin of an entire order batch. Then there is the operational drag. Every defect triggers a cycle of customer service tickets, photo documentation, and complex investigations into supplier batches. These failures also strike at the heart of customer retention. A first-order packaging defect permanently suppresses the likelihood of a repeat purchase. Every leaked drop of perfume represents a direct, unpluggable drain on the company's operating margin. The most common technical failure begins with a sourcing decision, buying glass bottles from one factory and pump mechanisms from another to minimize unit costs. These bell curves represent manufacturing tolerance ranges. Tolerance stacking occurs when combining parts that fall on the extreme edges of acceptable specifications, creating systemic failure. A 0.5 mm variance on a glass thread is enough to destroy the seal. Because components are often tested empty, this mismatch remains invisible on the factory floor. The flaw only emerges once the bottle is pressurized with liquid and subjected to the atmospheric changes of air freight. The liquid is forced through that microscopic gap and eventually breaches the collar. Standard visual inspections cannot catch this. It requires strict negative pressure vacuum testing to simulate real-world logistics and identify a compromised seal. Furthermore, if crimping machines are calibrated to incorrect torque specs, they will either deform the metal mechanism or fail to close the tolerance gap entirely. Mixing unintegrated suppliers based on unit cost alone is essentially paying for guaranteed tolerance failure. Even when the mechanical fit is perfect, a failure can occur within the materials themselves. Chemically, perfume is a volatile solvent, a complex mixture of high-proof alcohol and concentrated essential oils. When gaskets use low-grade rubber or cheap plastic, perfume oils break them down. Over months, the material will blister, swell, and crack. To survive shelf life, internal gaskets must meet FDA and EU standards for chemical resistance. A bottle passing a leak test on day 1 can still suffer catastrophic evaporation later if the materials are chemically incompatible with the formula. The atomizer functions as a calibrated aerosolization engine, governed strictly by the laws of fluid dynamics. The physical properties of a dense, oil-rich extrait are vastly different from lightweight cologne. To ensure an even spray, the pump's internal geometry must be matched to the specific viscosity of the fragrance formula. This diagram maps 3 mechanical variables: orifice size, actuator stroke length, and spring tension. On the left, an atomizer with insufficient spring force for a heavy formula creates a solid, clumsy stream. This under-engineering results in unpredictable squirting, or nozzles that permanently clog after only a few uses. On the right, high-tension springs drive the fluid through a perfectly calibrated orifice, rapidly accelerating the liquid into a uniform aerosol cone. Selecting an atomizer from a catalog based solely on its aesthetic completely compromises the user's defining sensory interaction with the perfume. While internal mechanics define the use, the external packaging defines the product's survival during global transport. Heavy, ornate metal caps communicate luxury in the hand, but during global shipping, they act as blunt weapons. This free body diagram illustrates the mechanics of logistics shear. Standard courier vibrations convert the mass of a top-heavy cap into lever force, concentrated directly on the glass neck finish. Visually impressive presentation boxes often exacerbate this by failing to physically grip the bottle. If the bottle micro-shifts inside its secondary packaging, vibration systematically shears the pump crimp apart long before the customer opens the box. The engineering requirement is straightforward. Transit packaging must immobilize the bottle at the base and collar. Beautiful packaging designed only for static shelf presence will inevitably self-destruct under the dynamic realities of modern logistics. Solving these issues requires shifting from fixing individual defective parts to embracing systemic engineering. This wireframe illustrates the sequence of a correctly architected system. It starts with verified glass thread tolerances, mating with chemically inert gaskets, driven by viscosity-matched tumps, and secured by immobilized caps. The performance of this total assembly dictates the product's viability far more than the unit cost of any single part. Reliable perfume packaging is a single, interdependent performance system, never a collection of isolated SKUs. This systemic approach means brands must ask critical engineering questions before a single piece of tooling is cut. A golden sample sitting on a desk is not evidence of production quality. Brands must require batch-specific testing data to ensure that mass production maintains original tolerances. These are the specific data points that define a professional QC document: vacuum pressure seal reports, full assembly vibration simulations, and AQL compliance certificates. Forcing suppliers to provide this engineering data upfront costs nothing, while discovering its absence post-production can cost millions. Mechanical perfection is the foundation of the emotional experience: the satisfying click of the cap, the fine mist, and the product's pristine arrival. In the prestige fragrance market, functional mechanical reliability is the ultimate protector of the brand's premium illusion and its profit margin.